Welcome to the second exercise of the course of surface water hydrology, and more specifically of surface water hydrology concepts. This exercise will handle the topic of surface runoff, and more specifically will apply the method of the unit hydrograph. As we have seen from our theoretical lectures, we know that precipitation is the main driving force of our hydrological cycle. The water falls onto the land, but some of it is lost and cannot travel towards the river. Partly it is lost by infiltration, partly it's lost by evaporation and evapotranspiration, but also other losses like initial losses, depression storage, or for example interception, account for some losses of rainfall and lead to the amount of net rainfall. Now this net rainfall falls all over the catchment or in just a part of the catchment and is not directly in the river. The processes that are describing how this net rainfall ends up into the river and how it is distributed over time are the processes that we refer to as surface runoff processes, and which we will handle today. As we also noticed during our theoretical lectures, we see that if rainfall falls all over the catchment, there are some areas, here designated in the darker yellow and red, where the travel time towards the outlet of the catchment, here at the triangle, is much longer than the areas that are blue on this figure. It takes much longer for this water that falls on these areas to travel towards the outlet. And this is also represented by this distribution over time of the amount of water in the river. The more area that actually contributes to the runoff at the outlet, the higher the actual flow will be. And we know that it is generated actually from different locations. And that is what we use surface runoff processes for, to have actually to account for this transport of water from a certain location to the outlet. Now, we will apply, of course, hydrological methods. We have also seen some hydraulic methods in our course, but the hydrological methods usually use storage equations to get a relationship between inflow and outflow. They also use the continuity equation, which is always valid, and which is described by the change of storage is equal to what comes in minus what goes out. Now the storage equation that we have can have different shapes. It will be a function of inflow, outflow, and then, for example, the first derivative of the inflow, the second derivative of the inflow, or the derivative of the outflow and the second derivative of the outflow. If we look at typical linear storage equations, we see that we have just a combination, so a summation of different terms that are also mentioned in the previous equation here, so inflow, outflow, and the derivatives, with just a factor that is used to multiply these terms. Now, if these terms ai and bi are constants, we are working with a linear time invariant system. And this is also what we will use now today in this exercise. We will assume that our system is actually linear and time invariant. Now the good thing about having a linear system is that there are two main properties that are always valid. It's proportionality, where we actually know that if we have a certain input, we get a certain output. That if the input is multiplied with a certain factor, we also need to multiply the output with a certain factor. And on the other hand, superposition is also valid, and this is just if we have a certain input with a corresponding output, and another input with a corresponding output, we actually know that if we sum up the input, we will also have a summation of the output. And this is very useful in case of a linear system, because in that way we can describe any input, so any type of rainfall or net rainfall in this case, by actually combining different response functions. And the most typical response functions that we have are the impulse response function, so the response to a certain input like this, very small over time, so very short, but with a value of 1. The step function and the step response function, and then also the pulse function, and then the result of this, the pulse response function. Always keep in mind that the pulse function, so the basic pulse function, has an amount of 1, so it's the time step of delta t, and the amount is 1 over delta t. Now, how can we combine these response functions to get to a certain input that we are using? Well, this is done by applying what we call convolution. So let's assume that this orange line here is our input, can be a continuous measurement of net rainfall, or first rainfall and then the derived net rainfall. But we can actually also see this as a continuation, so all different impulses that are infinitesimal small, but all added up after one another. And each of these slices actually has a mass of I tau, so the amount of rainfall or input in general over at a certain time tau, over a certain period d tau. And we know that this impulse has a certain response, yeah? And if we account for the amount of input that we have by applying proportionality, we actually get this response. Now, we don't have one impulse, we have all of the impulses after one another. So if we want to know the global response, we apply superposition, and then we get our integral, which is called the convolution integral. This is what we will be using when we apply the unit hydrograph. And our assignment today actually asks that for a river basin with an area of 27.4 square kilometers, the storm runoff at the outlet and the corresponding net rainfall of that given storm are given below. So we have a table here with all numbers within time, so time steps of 30 minutes. And at this specific time, we have a certain amount of net rainfall. Of course, it's during the first time step from 0 to 30 minutes, we have actually a net rainfall of 20 millimeters. During the second time step from 30 to 60 minutes, we have 21 millimeters of rainfall, and so on and so forth. The corresponding storm runoff at certain moments is 0 at time 0, 22.44 at time 30 minutes, and so on and so forth. Now the questions that are asked here are the following. In question 1, you need to determine the unit hydrograph of the given catchment of 27.4 square kilometers for a time step of 30 minutes for this storm. So we have the storm that was mentioned here with our time step of 30 minutes, which is very, very convenient for us. And it is asked to derive the unit hydrograph based on the net rainfall and the corresponding storm runoff. In question 2, you will determine the unit hydrograph for a time step of 1 hour. So we will go from 30 minutes to 1 hour based on the unit hydrograph that we had determined in the first question. We will also discuss the method and the practical applications of such conversion. In question 3, finally, we will use the unit hydrograph that we derived in catchment 1 based on a given net rainfall to determine the direct runoff or the storm runoff with this net rainfall. So these 3 questions we will answer in the following videos.